Welcome to EDU World Space.
In this question, we have a smooth sphere with a particle of mass m on the sphere. It's given a horizontal impulse of v meters per second. The first part of this question wants us to find the normal force between the sphere and the particle just after the impulse. So we know that right after the impulse is going to have a centripetal force of mv squared over r, which keeps it moving in a circle. This must be equal to the component due to gravity taking away the normal contact force as this acts in the opposite direction. So the normal contact force will act outwards. So we know that mv squared over r must be equal to mg minus n. And as a result, we can rearrange this expression for part A and say that n is equal to mg minus mv squared over r. Because we are assuming it is in circular motion, and the circular motion is produced by the resultant of the mg component, so the weight component, and the normal force. The second part of this question wants us to find the minimum value for the velocity in which the particle does not slip. So now we have to say that this is at the point that it doesn't slip on the surface of the sphere and it instead flies off the surface, which means that the normal contact force is zero because it's no longer in contact with the surface. Thus, we use this expression obtained from part A, and we can say that m, this time v minimum, squared over r is equal to mg. Minus n, however, n is equal to 0. So as a result, rearranging this expression, cancelling these m's and taking this r up to here, we can obtain that the minimum velocity is equal to the square root of rg. So this is our answer for the second part. The final part says that assuming the velocity is half of what it is in part B, what is the angle made by the radius at this point when it leaves the contact of the surface? So what we do is we apply the conservation of energy, which states that energy cannot be created or lost. So in this example, we say that the initial kinetic energy provided by the impulse plus the initial gravitational potential energy must be equal to the final kinetic energy, as there is no gravitational potential energy when it finishes down the sphere, as we've taken this to be the 0 point. So we can create an expression that says 1/2 mv squared plus mgh, this is the potential energy term, is equal to 1/2 mv, and this new velocity that we're trying to find, squared. So we know that the change in height is equal to r minus r cos theta, as it's we can see here r, we can see theta is here, so the height is the cos theta component. So h is effectively equal to r 1 minus cos theta if we factor out the radius. Subbing this expression now into here, and knowing that v is equal to v minimum, so what we've obtained here, divided by 2, so the square root of rg over 2, we can get an expression that says that 1/2 m, this v expression here squared, so rg over 4, plus mg, and then subbing in this value for h here, so r 1 minus cosine theta is equal to 1/2 mv f, so the final velocity squared, so the final kinetic energy in this case. When we draw the free body diagram, as in this diagram, we can see that in the final position, after applying Newton's second law, we get that mg cosine theta minus the normal contact force. So mg cosine theta is the component acting downwards, so perpendicular to the surface of the sphere, minus the normal contact force, must be equal to the final centripetal force. So mvf squared over r. And since we know that n is equal to 0 as it flies off the sphere, we can cancel out this term and rearrange this expression by subbing this into here to say that Rg 9 minus 8 cosine theta over 4 is equal to Rg cos theta. And therefore, plugging in what we know, we can say that cos theta, and by cancelling out these Rg terms, cos theta is equal to 3 over 4. So arc cos 3 over 4 will give us the angle, which is approximately 41.4 degrees as our final answer.